All right, well, I think we'll just go ahead and get started. Hello and welcome to Universities Fighting World Hunger Summit 2021, Session 4A, Innovations for Solving Climate Change. I'm Andrea Thompson, Associate Program Director of the UC Davis World Food Center. The World Food Center mobilizes the resources of UC Davis to promote innovative, sustainable, and equitable food systems. We bring together partners in academia, industry, and the civil sector to develop integrated solutions to the grand challenges of providing food for all, to propel California's world-class food and agriculture technology hub, and to promote cutting-edge research, educational, and outreach programs in food systems. Today, we'll hear from three experts of innovations in addressing climate change. Ben Holton, who is the Ronald P. Lynch Dean of the College of Agriculture and Life Sciences at Cornell University. Enid Partika, currently a PhD student at Michigan Technological University, and Lauren Shimek, the founder and CEO of Food Tech Design. As our panelists are speaking, please be sure to enter any questions you may have into the Q&A box in the Whova app. You can also upvote other questions, and we encourage you to do so. We will have some time at the end when we will address as many questions as possible. Now, please allow me to introduce Benjamin Z. Holton, who is the Ronald P. Lynch Dean of the College of Agriculture and Life Sciences and a Cornell University professor in the Department of Ecology and Evolutionary Biology of Global Development. An accomplished international scientist, his research interests include global ecosystem processes, climate change solutions, and agricultural sustainability. As a founding co-chair of the California Collaborative for Climate Change Solutions, Ben works with researchers from key research institutions to accelerate the translation of research findings into practical climate solutions. He also directs farmland carbon sequestration projects to improve crop yields and create new financial markets for farmers and ranchers. Ben has published more than 130 works, including peer-reviewed scientific articles, book chapters, and published abstracts as tracked by Google Scholar. As part of his mission to connect scientific discovery with the public, he is also a frequent guest on regional and national news programs. Welcome, Dr. Holton.
Thank you, my pleasure. Thank you, Andrea, for that great introduction. And it's a real pleasure to have this opportunity to speak with you a little bit about this incredibly complex challenge, this commingled challenge of climate change, greenhouse gas emissions, and all the people around the world who are still suffering from food insecurity and lack of nutrition. Each of those issues is what I would consider a grand challenge. Collectively, it's Herculean. What I would like to do today is just provide a broad framing on some of the opportunities, some of the innovations, some of the technologies that are shovel ready to be deployed in force to not only promote deep decarbonization of agriculture and make agriculture a major force in solving the climate challenge, but also assist in resiliency and nutrition. So I will focus on trying to discuss where there's some high-level concepts developing, and I will also present some of my own research evaluating soil carbon capture, working with farmers and ranchers. Next slide. So here's the issue. I like to call it the 10 by 10 by 2050 challenge. 10 billion people, that's an estimate if we were to project out the world's population by 2050. 10 billion tons of CO2 capture, that number comes from the Paris Climate Agreement. We know that in order to avoid the most dangerous interferences of global climate change on our food system, on infrastructure, on livelihoods, so on and so forth, we have to seek pathways to decarbonize energy and manufacturing, slashing emissions in half globally each decade moving forward. And, heavy on the and, we have to extract at least 10 billion tons of carbon dioxide each year by 2050 and hold that constant, perhaps even increase it some through 2100. We can no longer avoid the worst interferences by slashing emissions alone. It's going to require both emissions reductions and carbon capture. We also have to recognize that we have to find pathways to feed a growing world population. Already it's estimated that 2 billion people on the planet suffer from some form of micronutrient deficiency, and around 800 million suffer from hunger. Big challenges, commingled challenges, the 10 by 10 by 2050. That's what's in front of us. Next slide. Well, I'm going to focus just on a few key ideas that are starting to emerge, some of which are tried and true sort of approaches to managing soils, but others are involving new innovations. I call it the gigaton economy. We're all aware of the gig economy, but the gigaton economy is a billion-ton carbon removal economy through which carbon becomes the commodity of our time. There's a lot of discussion right now about soil carbon sequestration, plant breeding opportunities, but what we really need to focus on, in my opinion, is the notion of carbon capture with benefits. That carbon capture happens when we engage in the right kind of practices, seek out innovations, things like CRISPR to create photosynthesis that's even more efficient in our cropping systems, engage in soil amendments. But the benefits that come to our farmers are those that will probably lead the way toward rapid deployment and uptake. Policies are going to be critical, carbon pricing can be critical, but the benefits of some of these practices in terms of enhanced nutrient use efficiency, reduced fertilizer costs, water benefits, these are the kind of innovations that increase bottom lines and allow for some scalability in the agricultural sector. Next slide. So now I'm going to talk to you about one particular technology which is focused on idea of taking carbon dioxide and rather putting it into an organic form, which can have benefits, trapping it as an inorganic carbonate in the soil and in water that allows that carbon to be extracted for thousands, if not more years. One of the challenges of soil carbon farming, as we call it, is that a lot of this carbon is mobile. Microbes are efficient at reprocessing some of the material. And so we need to find not only pathways for organic carbon sequestration, but inorganic carbon sequestration. You can hit the button. So the idea here, and you can just go through all of them since I'm not in control, thanks. So the idea here is taking advantage of a technology that was invented on planet Earth over 4 billion years ago. That's rock weathering, which is capable of sequestering CO2 each time mineral dissolution reactions take place. In essence, calcium silicate rocks combined with CO2 in water to make carbonic acid, which is then converted to bicarbonate in the soil and can be stored as 2 moles of carbon per reaction as bicarbonate or as calcium carbonate. This can ultimately make its way to the ocean. And the notion here is to repurpose waste streams from the mining industry, aggregate mines, and start to put that into the soil. Now, this sort of material is volcanic in nature and has incredibly good properties in terms of nutrients, micronutrients like iron and zinc, also calcium, potassium, and other nutrients that our farmers need. So we've been testing this idea across a range of sites in California to try to see if we can perfect our ability to catalyze what we call negative carbon emissions or carbon capture with benefits. Next slide. So these are preliminary results from a trial that we have been undertaking across, again, more than 100 acres of farmland in California. We're working across diverse types of crops, including corn, alfalfa. We're working in orchard crops with almond. And these results are based on our corn trials that took place just outside of UC Davis's campus across 5 acres. The preliminary results are, you can see the control where we added no rock dust. You can see the metabasalt where we added around 20 tons of rock dust, and then the olivine plus metabasalt combination. We are seeing more than a doubling of carbonate formation. This kind of carbon sticks around again for thousands of years or longer with these amendments. So it's really intriguing results suggesting that when we repurpose rock dust, in this case from a local mine, where it is just material that's not providing any benefit to the mine, it can provide incredible carbon drawdown in the form of what's called enhanced weathering. Next slide. And here's where the benefit comes in. We are finding an 18% increase in alfalfa yield across some of our treatments. Now, these are preliminary results, and I don't want people to get too excited. These trials have to take place for a few years before we have confidence, but we are seeing an 18% increase in alfalfa across more than 17 acres of trials. So this is not just some small scale experiment in a quarter acre. These are on real live farms that are using real farm equipment, and then we're just estimating yield with them to understand how the rock can provide benefits. We're not quite sure on the mechanism. We have a few ideas I'd be happy to talk about, but we are seeing so far a positive result in terms of crop yield. Next slide. So that in mind, I now want to focus back out on the big picture of where technology and innovation can go with agriculture. And this fits with the thesis that agriculture can be an incredibly powerful weapon against climate change. This is a paper that's in review where we have assessed all of the various technologies that have already been demonstrated and what their scalable potential could be by 2050 using a global food system model. All told, if you were to add up all these technologies at kind of 100% capacity of the land area in cropland, in this case, it would be about 12% of Earth's land surface by 2050, we estimate 30 billion tons of negative carbon emissions capacity is possible. So what are some of these technologies? Well, hydrogen power, displacing natural gas to create Haber-Bosch fertilizers, that can get us to a full 1 billion tons of carbon reductions. No-till and ocean no-till, as they call it, for agricultural seafood production, that can get 2 to 3 billion tons. Coated fertilizers and precision cropping systems scaled out could reduce nitrous oxide emissions, getting us an additional 1 billion tons. Dairy digesters that repurpose dairy manure in the form of natural gas production, that gets us around 4 billion tons globally. And then we get into things like microalgae production, seaweed, alternative feed for livestock. And in this case, this can reduce methane emissions and continue to produce high quality product, high quality milk, getting us to about 4 billion tons. Agroforestry is an area where we find the most potential. Agroforestry intercropped can get an estimated 10 billion tons. And then finally, we get into regenerative agriculture and food waste, which gets us another few billion tons. So all told, this is a capacity. There is a huge difference between where we are today and getting these to scale out. This isn't something that's going to happen with a snap of a finger. But the exciting thing here is it says the capacity is there for agriculture to not only contribute to emissions reductions, but to generate substantial negative emissions, which is needed if we are to achieve the goals of the Paris Climate Agreement. So thank you very much. Happy to take questions in the Q&A.
Wonderful. Thank you so much, Dr. Holton. Now I'd like to introduce Enid Partika, who's currently a PhD student in environmental engineering at Michigan Technological University. Before her time at Michigan Tech, she received her MS in analytical chemistry and her bachelor's degree in environmental systems and environmental chemistry. Her previous research as a Carbon Neutrality Initiative Fellow at University of California, San Diego encompassed the design, construction, and operation of a student-run, community-scale anaerobic digestion system that converted over 25,000 pounds of food waste from university restaurants and dining halls into hydroponically grown food for the campus community in a single year. For her work in anaerobic digestion, Enid received the 2019 Lemelson MIT Student Inventors Prize and University of California Office of the President Student Leadership Award. Enid's experience also expands to HPLC method development optimization for the production of succinic acid for bioplastics and biofoams with algenesis materials, as well as bioplastic and plastic degrading reactors with the Dehane Lab at Scripps Institution of Oceanography. As a graduate student at Michigan Tech, Enid will be working with Judith Perlinger and Noel Urban on developing a QAPP for PBC analysis of the Great Lakes fish tissue in collaboration with the Keweenaw Bay Indian community using CGQQQMS. Welcome, Enid.
Thank you very much for that introduction. If you could go to the beginning of the slides, please. So today I'll be talking to all of you about the Bioenergy Project, where we have, I was collaborating with Engineers for a Sustainable World at UC San Diego, as well as with Rogers Urban Farm Lab, where we combine our expertise in urban agriculture and sustainable agriculture, hydroponics, aquaponics, and computer science to develop our anaerobic digestion system. And with this anaerobic digestion system, we worked on converting food waste not only to energy, but also to fertilizer for biogas. And that's the correct slide. Yeah, you can start out there. All right, and next slide, please. So right now, the world is facing a food, energy, and climate trilemma. In just the United States alone, every single year, over 168 billion pounds of food waste is thrown into landfills. And not only is this one of the main contributors to climate change, but this is also one of the main contributors to the filling of landfills throughout the United States. And even though this is happening, over 1 in 6 Americans are food insecure. And this is only expected to increase with rising global population and energy and food demand. And so this problem doesn't only, while this focuses on the United States, it's not just the United States, but also, this problem is pervasive throughout the world. Next slide. And so our solution to this at UCSD was to use aquaculture and food waste to convert these wastes through anaerobic digestion. Maybe if you could click the slide, there's actually a little bit of a video, please. So we'll use anaerobic digestion to convert into biogas energy, which can be used for not only electricity generation, but for cooking and for heating, since biogas, the main component is methane. And we also use the liquid waste products to create fertilizer, and this fertilizer can be used in as a liquid fertilizer in orchards or in hydroponics, both of which we did at Rogers Community Garden, and to grow, greens, broccoli, different stone fruits, and all of this was completely automated using a Raspberry Pi microprocessor, where you can receive nutrient data as well as temperature and process controls for your digester directly to your phone or to your computer through a website. Next slide. And so this technology encompasses the UN Sustainable Development Goals of sustainable cities and communities, establishing quality education specifically on food waste mitigation and renewable energy. And it also provides affordable and clean energy in the form of biogas, and helps the UN goal for zero hunger by providing communities with the means to produce their own food from their food waste. Next slide. And so our system specifically, while a lot of industrial composting can only take certain, vegetables or fruits, our system is actually able to take all types of food waste. And with some preliminary trials, we were actually able to break down some small concentrations of bagasse and paper products with our system. And so it's also very easily assemblable. We build our digestion system with the consumer in mind from materials that really you can mostly get from your local hardware store. And so this makes this technology more accessible to the common person. In addition, our integrated hydroponic system has provided the means to produce your own fertilizer and thus grow your own food directly from the waste that you produce. And our system also is designed off of the principle of using as little electricity as possible. So we're actually able to power it off of 100% renewable electricity We were mostly powering off of solar electricity with our solar water heater that you can see in the center here. And we were also powering it off of some of the biogas that we can produce. And overall, with our prototype, we were able to use over 50% of repurposed materials. And not only that, being at a university, we wanted to encompass the goals of our community. And being in a university, that goal is education. So we really we wanted to integrate not only the technology, but also the education that goes with it. We wanted to be able to educate people on the advantages of food waste mitigation and the advantages of anaerobic digestion, not only to sequester carbon that would otherwise be, just emitting methane in a landfill, and instead utilizing that to produce energy and produce food. Next slide, please. And so we developed two scales of system. We have our family scale, which converts 30 pounds of food waste into 24 pounds of greens, 1 pound of fish, and about 14 hours of cooking with 1 kilowatt stove over a month-long period, all the way up to our community scale, which converts 2,000 pounds of food waste into 120 pounds of greens, 10 pounds of fish, and 14 hours of cooking for 65 1 kilowatt stoves. And so this really demonstrates that, while this is a small scale energy, it does have significant local impacts, especially, for developing nations where they may not have a reliable source of energy or cooking fuel that's safe to have inside of their homes, or, the ability to produce their own food using their own means. And so this technology really provides that, for the community and for the individual family. Next slide. And so on the UCSD campus, we not only wanted to develop this technology, but also create a system to be able to have it continue in the long term. And so we worked a lot and are still working with the university and the administration to be able to collect food waste from these restaurants and convert it into the biogas and into the fertilizer. And we worked with the anaerobic digestion system as well as the composting system at the community garden on campus, where we converted over 70,000 pounds of food waste into usable products such as fertilizer. And in doing so, we also sequestered an estimated 5.6 metric tons of carbon dioxide. And this is just in a single year from a single system. Next slide. And in doing so, we also wanted to create a sustainable and equitable business model. How could we transfer this technology to our community? And so when we produced our Digesteroponics project, we immediately are servicing universities, but also aim to reach out to residents, in rural areas or in off-grid areas. And through our university community partnerships, we're actually able to partner with a community garden in Southeast San Diego to be able to, transfer this knowledge to them and also, have the community learn about anaerobic digestion and also receive insight on how to build and maintain such a system. And so in doing so, we're helping establish that community hub of learning, as well as this community hub where people could bring their food waste and then use that to create fertilizer for their garden. And this also transfers back to us because the community also can provide really valuable feedback on, what works for them, what types of crops are best to grow, how much energy they might need for a particular application. And so with that knowledge, we're better able to improve our system and, make it work for more communities. Next slide. And so some of the examples of more the educational aspect of our project. So on the left-hand side of the screen, you can see that some of our interns working with the system, learning how to use it. We also had the wonderful opportunity to go to Tijuana and help a community center construct a water treatment system to help actually filter the water enough to be able to use in a local garden. And also on the educational aspect, during the COVID pandemic, we were able to, we wanted to continue to reach out to people. And although people couldn't always meet in person, we created a webinar series that was able to continue the learning experience by having workshops where we would film ourselves working on the anaerobic digester or operating the hydroponic system or aquaponic system, showing people how to grow food from this food waste. And it was really successful. I think we reached up to 100 participants for one of the videos. So you know, it's been interesting being able to reach wider global audiences with our technology. And we're also able to develop relationships with community-supported agriculture organizations where we were able to use our fertilizer to grow onions and other produce, peppers, loquats, and be able to package that to deliver to the community. Next slide. And so while we focus a lot on our local scale, our technology is transferable in that, you know, with every community that we provide an anaerobic digester to, and for every person we educate about this, the benefits of the system, you know, that's one more person, one more community that is able to reap the benefits of this food waste mitigation technology and really be inspired to be able to produce not only their own energy, but also their own food. And so it enables an aspect of self-sufficiency. And so this can be transferred, you know, not only at UC San Diego, but also throughout the world. Next slide. And so overall, the Bioenergy Project is aiming to solve the trilemma of food, energy, and climate through a modular and scalable system from individuals up to universities and communities, and is relieving food insecurity through community education and empowerment. Thank you.
Thank you so much, Enid. That was great. Our final presenter, before we address questions, is Lauren Shumack, who is the founder and CEO of Food Tech Design. As a PhD food scientist with over 17 years of food design, product development, and innovation, including at IDEO and General Mills, she creates breakthrough food and beverage products that tap into people's unmet needs and desires while being grounded in manufacturability. Lauren's personal passion for food, deep technical expertise, and design thinking know-how places her at the innovation intersection of food, science, and technology and design. Lauren holds a PhD degree in food science and a BS degree in biochemistry from the University of California, Davis. She has served on the board of directors for the Institute of Food Technologists and is a former adjunct faculty member in the Department of Food Science and Technology at the University of California, Davis. Welcome, Dr. Shumack.
Hi, thanks everyone. I'm really excited to talk a little bit about a toolkit for climate change innovation and really to complement the other two speakers in this session. So if you'll go to the next slide, please. I'll just dive right in. When preparing for this talk, I was thinking, how should we innovate to address complex systems challenges? And those challenges, as Enid just mentioned, are many, food waste, food insecurity, climate change, and more. And one of the ways we feel strongly about is by introducing new tools to students and to professionals in the space to help them think differently about these problems. Next slide, please. So I teach a course with another professor, Dr. Charlotte Biltikoff, called Design Thinking for Food. It's kicking off in a week, actually, this spring quarter. And it's a graduate level course where we introduce the toolkit of design thinking and we use it to address a particular food systems challenge. For the first 2 years of this course, we addressed food waste in the dining commons, which I'll talk a bit about in this session. And the last 2 years, or this year and last year, we focused on food insecurity. This course, again, is starting this next week, spring quarter, and I have the website at the end of the presentation. If you go to the next slide. You might be wondering, what is design thinking? If you're familiar with companies like IDEO or have seen it out in the media, you might know that it's really at its highest level, these 3 circles. It's thinking about people's needs and desires. It's asking the question of how do we find solutions that are also viable for businesses? And then finally, it includes the technical lens. Can we do something that's actually feasible? And it looks through all of these lenses simultaneously. The one difference in design thinking than perhaps some other innovation toolkits is that it always starts with people and it's truly human-centered. If you go to the next slide, please. I'll talk a little bit about that. When I mention the word human-centered, it's really about building empathy. And so you might be wondering, well, what does that have to do with climate change or with food waste? Well, there are always people involved in all of these complex problems. And what we do with design thinking is we encourage people to not only listen to what people are saying and watch what they're doing, but go one level deeper to understand what they're thinking and how they're feeling so that we can truly understand the heart of the problem and be empathetic towards their needs and design to that. Next slide, please. So we see design thinking as a toolkit. You might have seen it as a process. And in the 10-week course we teach at UC Davis, we do teach it sort of one phase after another, beginning with insight and inspiration, followed by synthesis and strategy, design and prototyping, and communication and storytelling. But the best practitioners really do see it as a toolkit and sort of use these different tools as they see fit to address problems. On the very bottom of this framework are the outcomes of each of these phases. So observations, inspiration, and stories, synthesized into insights and opportunity areas, which then springboard into ideas and prototypes, and finally, in our course, culminate in some kind of presentation or a website or other communication tool. If you'll go to the next slide. I'll briefly just talk about our course in 2016 and 2017 when we addressed the challenge of food waste in the UC Davis dining commons. Next slide, please. Our course began, as I mentioned, in the insight and inspiration phase, and that's where we look out into the world to really understand people. And we also look out into the world to see, are there other interesting solutions going on in adjacent categories or other spaces that might inspire us to think differently about our problem? So our student teams conducted over 20 in-context interviews with students and staff. So people who were using the dining commons, people who worked at the dining commons, people who were behind the scenes, planning, sourcing, creating all the infrastructure that makes the dining commons run smoothly. So we were looking at all of those key stakeholders and really trying to understand where were the pain points, what were the challenges, and what were the unmet needs that weren't being met today. Next slide, please. It's not enough, as I mentioned, to just talk with people. We really have to spend time synthesizing it and turning it into an actionable strategy. And so that's what our students did. They spent time framing the problem of food waste into opportunity areas for design. Next slide. From those opportunity areas, they created ideas. Some of them were product ideas, some of them were new behaviors or plans. And in part of this process, they brainstormed actually hundreds of ideas. They chose the ones that were most promising, and then they rapidly prototyped them. You can see some really kind of rough prototypes that really help answer and raise good questions that help them evolve their ideas quickly. Next page, please. And finally, in the last piece, communication and storytelling. It's not enough to have a great idea. You really have to get people around you on board and help them understand the idea so they can embrace it and adopt it. And so we do spend time in this course on communication and storytelling, where they actually, in a human-centered way, create their presentations with the audience's needs in mind. Next slide. So a few key insights from our course on food waste on campus. The first one, if you'll click through, please. UC Davis has an all you care to eat system. And that's a system where you swipe your card and you go in and you can choose kind of anything you want and how much you want. And really our students looked at that, talked with people and realized that system is designed to generate waste. It's just inherent in the way that it's set up. Next, please. We also found that it was a misstep to treat food waste as purely quantitative and technical. Engineering and technology are definitely part of solving food waste, but it's not the only part. Again, going back to those three lenses, we really must consider people as well as the technologies and the quantitative piece to help solve the problem. Next, please. It's also not a problem of just ignorance or indifference. We saw that there are some great programs trying to educate students about food waste, sometimes at the dining commons when they're there. And that certainly is important, but again, it's not the only solution. And the last slide, please. And that's partly because food waste is not intentional. It occurs in the course of other activities, and not wasting has to be connected to other unmet needs to rise up sort of in that priority. If you go to the next slide, one of the things our students were thinking about at UC Davis, many of the students that use the dining commons are first-year students, not all, but many. And so we really asked ourselves in those interviews, what are the unmet needs of first-year students in the dining commons? And you might think, oh, you know, when you're, especially in the beginning of the year, it might be about making friends. It might be figuring out where I'm going to sit and who I'm going to meet. It might be figuring out, oh, am I going to choose something healthy or something really indulgent? But one of the core unmet needs that our class uncovered that's really linked to food waste is finding something that you like to eat. And it sounds so simple, but when people find something that they don't like to eat, they often throw it away. And in this setting, they choose something else, or they might choose a whole bunch of things, hoping that they might like one. And inevitably, that often turns into food waste. So we found that to be a really interesting insight to tap into as we built our solutions. If you go to the final slide. Again, as I mentioned, in 2019, the class changed challenges from food waste in the dining commons to food insecurity on campus. And our course starting next week will also be addressing that. Again, thinking through the lenses of business viability, technical feasibility, but most importantly, through people's desires and unmet needs. So with that, I'll go to the very last slide. And you can see if you're interested in the course, feel free to look at our website. I'd love to turn it back over to Andrea for our Q&A.
Wonderful. Thank you so much, Lauren, and thanks to all of you for those great presentations. We do have a little bit of time, despite our the agenda on Whova. We actually have until about 3:20 for this session, so we have a few minutes to answer a few of the questions that are out there. And then I will just make one comment after that. But firstly, the first question we have is, are there any known side effects on health using hydroponic farming because it uses artificial lights or it's grown in a controlled environment? And does anybody have anything to say about that?
Well, at least in our system at the garden, we weren't using the hydroponics indoors. While I know that I'm not entirely sure exactly on the large scale indoors how much carbon, say, is used for the electricity versus, you know, the benefits to the food waste outputs. Maybe Benjamin could provide more insight on that. But I know at least for our system, you know, hydroponics doesn't necessarily have to be indoors. We were using it kind of as a hybrid, I guess you could say. We were using the digestate waste as a fertilizer, and so that sort of acted as the recirculating liquid in our hydroponics system. And so hydroponics has been shown to have higher yields than traditional agriculture, and it also is a good way to save water, for example, because you recirculate the water throughout your system, and it isn't lost to evaporation quite as much as, say, you know, directly flooding fields or other agricultural methods. And so with that, you know, we were able to use the liquid fertilizer in the digester similar to that. Maybe if Benjamin, you wanted to provide kind of a larger perspective on that.
Well, I think you answered it really well. There's an incredible amount of work right now on the use of AI, machine learning, robots, sensors in all of these kinds of sort of controlled environment growing facilities. And if it's done correctly, locally, you can radically reduce the carbon emissions. If the energy mix is based in renewable, of course, then you find a really good pathway. If the energy mix is based in fossil fuels, then you're going to still be using a considerable amount. But the work on indoor sort of, whether it's hydroponic or just indoor controlled growing facilities, is really taking off in certain areas. And I see that as an important part of the solution set, although it's hard to see how it could become, globally the answer to many of the world's challenges with food production. It will be in part locally, I think, pretty important.
Ben, this one came in actually during your talk. This says, with the CO2 and other greenhouse gases being added into our atmosphere due to agriculture, combined with the need to increase food production as population increases, do you have any ideas on how to accomplish carbon sinking while increasing food production?
Yeah, that's a great question. And in fact, that global systems model result I showed of 30 billion tons of negative emissions first satisfied the caloric intake of 10 billion people and adopted the scalable footprint of total land area that would be needed, and then deployed the technologies on top of that. So the answer is yes, we can do all those things in principle. Now in practice, and I was talking about capacity, and the difference or the delta between what we can do and what we're doing is enormous right now. And so once we get our incentives aligned, like things that are happening with the Biden administration right now, carbon banks, crop insurance premium, these are all critically important to scaling out these innovations. But there is not necessarily a trade-off, which is an interesting finding when you run some of these capacity models. Yet, when it comes to people and their decision-making, it's not always super predictable. I think we heard some good discussion of that in design thinking.
All right, and then third question here is, do you recommend these technologies should be installed centrally at each farming location for great benefit and affordability, or otherwise? I guess maybe that's geared maybe towards either you or Enid.
Well, ours is all based on a land footprint model that is spatially aggregated down to the grid cell of like 100 by 100 kilometer grid cell. So in that sense, we just say, where is it possible to do these? But we're very far from the spatial mix of modeling that's necessary to really deploy the true economic value relative to local conditions. I think that's going to be the next iteration of some of the modeling, and then demonstrating how that works is probably more important than the modeling work itself.
I would say that at least in terms of local scale anaerobic digestion, in terms of farms, I know that one of the main beneficial uses of anaerobic digesters, at least lately in the state of California, has been actually at manure or at like dairy farms, for example, because they can use the manure to generate a ton of biogas. And so in that, local sense, I suppose it depends on the operations of the particular farm. But, in terms of, small scale organic farms, for example, they could absolutely use a digester as well. While vegetables, for example, don't have quite as much of a biogas return, the fruits and vegetables have a great micronutrient profile. If you have say more food waste that is more carbohydrate rich, for example, you can produce more biogas. It really depends on what type of agriculture you have, will sort of determine the different benefits. So more fruits and vegetables, more meats or fish, for example, you can have more nitrogen that way. So yeah, I think there's a lot of opportunities on the local scale to really design a system that works for you. And a lot of like say if the fertilizer is deficient in nitrogen, for example, there's a lot of natural ways that you can supplement that fertilizer, for example. That's why we started some of the aquaculture, actually, because fish waste is high in nitrogen. And so we can use that as an organic fertilizer supplement. And so, yeah, I think it's definitely possible on the large, on the local scale to implement, technologies that can capture at least some carbon and be able to produce something in return. Just a matter of ingenuity, I guess, and working with the local farms and communities.
Great. All right, well, thank you all. I think actually we're right on time here, because at this point I need to thank everybody for attending today's summit. We hopefully everybody's going to come back tomorrow, and we're hoping that you will preview tomorrow's sessions and look it all over and choose what you want to attend. And then join us at 20 after in just a few minutes for today's closing session with the University of California's President Drake. And as a reminder, all sessions of this summit are being recorded and will be available to all attendees on Whova for 3 months via the website, or for 6 months on the phone app. So even if there are sessions that you weren't able to attend that you were hoping to hear from, you'll be able to revisit those. So we hope to see you again at the closing session today and tomorrow morning. All right, thank you everybody so very much.
Thank you.